podcast on physics for students. In a world often shaken by turbulence, both natural and man made, it is worth pausing and reminding ourselves that there is a grander, more patient story unfolding, one written in starlit and stitched across millennia. And in this vast cosmic backdrop, India's tryst with the sky is as old as civilization itself. Today's episode, Astronomy and Indian Society, is not just about stars, planets, and galaxies. It is about how the cosmos has shaped culture, guided migrations, structured calendars, and inspired generations across the Indian subcontinent. It is a celebration of the timeless bond between observation and imagination, between science and society. We are deeply honored to be joined by someone who has not only peered deep into the universe with space telescopes, but has also looked inward into our histories, our myths, and our social evolution with equal scientific rigor and empathy. I am speaking of none other than Professor Mayank Vahia, one of the India's most respected astrophysicists. Dr. Vahia earned his PhD in astrophysics from the TIFR in 1984 and served there until his retirement in 2018. At TIFR, he was instrumental in building and operating 4 space telescopes flown on American, Russian, and Indian satellites, a rare and remarkable achievement itself. But that what truly sets him apart is his deep engagement over the last 2 decades with the history of science, astronomy in ancient India, tribal and rock art astronomy, and the evolution of human societies. From decoding the skies of megalithic cultures to guiding India's astronomy Olympiad programs, his contributions straddle both cosmic inquiry and cultural insight. Dr. Vahia has also served on numerous national and international academies, councils, and advisory boards. After retirement, he founded the School of Mathematical Sciences at NNIMS, completing a 3-year journey of academic leadership. To all our loyal subscribers and first-time listeners, thank you for being with us. As always, we invite you to stay curious, ask questions, and share these conversations that illuminate our understanding, not just of the skies, but of ourselves. Let us begin our journey now into the stars through time, and with a warm welcome, Sir Professor Mayank Vahia, a warm welcome from Physics for Students.
Thank you very much, Shaunak. I hope my voice and my slides are clear to you. And
Absolutely.
Thank you very much for inviting me. It's my pleasure to be here. And what I'm going to do today is to talk to you about origin and growth of astronomy in India. And I will show you various examples of activities at various levels that have happened in India and take a stock of how astronomy has grown in India from its ancient times to modern times.
Right.
So we
Okay.
are talking about origin and growth of astronomy in India. And what I was saying was that the technological sophistication of a culture can only be seen, archaeology can only give you the technological sophistication of a culture, while intellectual growth needs to know the literature and art and so on. And while myths, etc., get lost, religion evolves, literature, of course, changes. Astronomy and mathematics are 2 subjects that actually hold on to the culture's original identity, and they give you a lot of information about how the cultures were thinking, and that's what we are going to explore. And the first thing you realize is that very early human beings, in fact even Neanderthals, had their image of Mother Earth and Father Sky, because Mother Earth is the one that gives life, and Mother Earth can give life only when there is rain, so the Father Sky has to seed her. And that idea is one of the oldest religious beliefs that exists. Then
Sir,
the
we have
drama of
one,
Thunderbolt, etc.
sorry to interfere, sir. Sir, we have one question coming from Gautam. He is asking you, sir, what is the actual meaning of astronomy?
Astronomy is the study of stars and sky.
Okay, yeah. Gautam, so sir has
Astro
told.
is
Yes, sir.
okay.
Please go. Yeah.
So then you have this Mother Earth and Father Sky is as old an idea as ever. And therefore, science, astronomy is often considered the first science because people from very early period realized the nature of sky, its stability, its patterns, etc. And therefore, they studied these things very early, even as they were still doing their basics of learning of farming. The first formal science probably was astronomy. One can argue that it is botany also that came with that, but that's another thing. Then the sky has fascinated people from a long time, and the skies have been seen as heaven and earth, like I said, and events and activities in the sky have always been of fascination to us. There are interesting, for example, rock art. There is a rock art in South India, where you can see that there is a drawing on the ceiling of a cave, and if you draw the ceiling properly, it looks like this. There is a ladder in the middle. There is apparently a body over here, and there are all kinds of patterns over here, and you can interpret this any way you like. I mean, there will probably be dozens of interpretations as to why the ladder is in one place, the waves are on the other side, there are lines on this side, but this mountain range and they go halfway, and there are lines and all that. So one can write essays and essays on what this probably meant, but we don't know for sure because we only have the raw card. Then there are raw cards like the one that on the right side, where you can see the great superhuman holding the sun and the moon and so on. And this concept has been as old as human imagination. Then there are, for example, there is an Orion constellation. If you are familiar with the sky, then there is this three stars of Orion, the very famous belt of Orion. And then there is Taurus and there is Pleiades. Pleiades has this is the only clearly visible cluster of stars. So there are 6 or 7 stars visible in a cluster. If you have good eyes, you can see as many as 20 in the cluster. And then there is Taurus, and then there is Orion. This same region of the sky is interpreted completely differently depending on which culture you are talking about. So it is called Mrugashirsh in India, or the head of a Taurus, head of a bull. It is called a marriage festival in some Indian tribals. It is called a farming scene among Gonds. It is so Warlis call it a marriage festival. Gonds call it a tribal hunting farming scene. Some others call it a hunting scene. Some people in Europe see it as a hunting scene. In Mayan, it is seen as a turtle. In Southeast Asia, it's a turtle. In China, it's a horse. So the same region of the sky is seen differently depending on what your personal preferences are, and that is what makes astronomy so much more fascinating and so much more culturally dependent. The same region of the sky is seen as a horse in China, as a horse rider in China is seen as a hunter in Europe, and so on and so forth. And there are tribes that even actually look at this Taurus, the bull, and create traps for catching birds, which they think are the way in which the gods themselves to catch the birds and for their own food. And so they designed this entirely based on the what they see in the sky. The same region of the sky is interpreted differently by different cultures. And who uses astronomy? Lots of people use astronomy. Artists, of course, use astronomy. Farmers use astronomy to define monsoon seasons. Travelers use astronomy for direction. Calendar makers use astronomy for calendrical purposes. Priests, and of course, astronomers who are fond of knowing what the sky is. There are various aspects to the sky. Now, the first thing that we know, let me try and show you the pictures individual. This would have come as an animation, but anyway. So, the first thing we know is that the Earth goes around the sun, and as Earth goes around the sun, we in June we get summer in the northern hemisphere. Then in March we get this equinox where the day and night are equal. In December we have winter in the north and summer in the south, and then another equinox. So this cycle goes on annually. Once in every 365 days, the sun comes back to the same point. If you look at that point from the Earth's perspective, then what you will notice is that if you're standing here and the east is here and the west is here, in summer months, the sun rises to the north of east and remains in the sky for a long time. In the winter months, the sun rises to the south of east and it remains in the sky for a shorter time. And of course, in especially in the Indian subcontinent, you get rains when the sun crosses the equinox period, or monsoons are close to the equinox period. As a result of it, people define seasons. People very early recognize the fact that the rising point of the sun defines what the season is going to be like. And then we have the moon, which is a very dominant object in the sky. And that moon, so if you take this as the image of the as the movement of the moon, then if the sun is coming from the left, then you'll get new moon when the sun and moon are in the same side of the earth, and you get full moon when they are on opposite side. And then there are various crescent and full moon. If you start with day zero, then you get waxing moon early first quarter and so on, and eventually after 29 days, the moon comes back to the same position. And that is what forms the basis of astronomical ideas. Then there are, of course, the sunrise point changes over a period of time, because as the earth goes around the sun, in January the sun appears to be in the constellation of Scorpius. In May it appears to be in the constellation of Aries, and so on. So around 12, there are 12 special constellations in which the sun seems to move, and we call them the zodiacal sign or rashis. Apart from that, so that there is this issue, then there is eclipses that come every now and then. Comets come every now and there are nine objects, only nine among all the star objects that you see. There are nine which go around in the sky. They are not stationary with respect to other stars. So, Sun, Moon, Mercury, Venus, Mars, Jupiter, and Saturn. Seven of them are the ones that move, and therefore we get 7 days of the week based on these seven moving objects, which we call planets. Then there are comets and so on. And then there is a very curious other thing that happens, which is that the Earth's orbit precesses. In the sense that the Earth orbit is pointing in one direction. Currently, it is pointing at the Polaris star, but this axis keeps rotating. So over a period of 14,000 years, over a period of 25,000 years, it comes back to the same point. But for example, today we have Polaris as the pole star. 3,000 years ago, it was Thuban that was the pole star. 14,000 years ago, it was Vega that was the pole star. And this circle goes on. And what that circle means is that the point at which the equinox or solstice occurs varies. So, for example, vernal equinox was in Leo in 10,000 BC. It was in Gemini in 5000 BC, and today it is in Pegasus. So the constellation in which you get vernal equinox is varies from because of the precession of the Earth, and this has been noted in many literatures about which is the day on which the vernal equinox happens. I would have shown you the same slide about solstice, but the point is the same. All these can be tracked very easily using a stick in the ground. And because that stick in the ground has such an important observational ability, we have a special name for it. We call it a gnomon. And what I have here is a shadow of the gnomon. So imagine that at the center of this picture, the stick, the gnomon is coming out of the screen. Then in winter, when the sun is in south, the shadow of the gnomon in the morning will be in this direction. Sorry, this is the east. So when it is winter solstice, the morning shadow will be in this side, and it will travel like this. In summer, when the sun is at the northernmost point, the shadow will move like this. So it will move for one day across, and it will move one up down once during the entire year. So the movement over 6 months is from topmost to bottommost. The movement during the day is from right to left. And so sundials basically are the same principle done in a little more fancy way. But essentially, a stick in the ground is enough to tell you um, the seasons and so on. So if you just keep a stick in the ground, you can tell the time of the day as well as the month or the month of the year when when the monsoon is going to come, etc. You can predict using all these things. In latitude, if you live in a city which is to the north of Tropic of Cancer or south of Tropic of Capricorn, you essentially still will never cross this gnomon point. And so, for example, in northern hemisphere, you will only have some shadows which are to the north of the building. And if you have a building in north of Tropic of Cancer, say in Delhi or something, you will never get a shadow towards the south in Delhi. It will always be towards the north. And similar Tropic of Capricorn will be the other way around. So where as long as you are between Tropic of Cancer and Capricorn, the shadow, you will actually have one day when there is zero shadow at noon. But if you're north or south of Tropic of Cancer, or north of Tropic of Cancer or south of Tropic of Capricorn, you will never have a zero shadow day. Then there are other things. We know that an hour comes from the sun. We know days obviously come from the sun. The week comes from the moon. A quarter of the moon is 1 week. Fortnight is a more common unit, which comes from full moon to new moon to full moon. A month obviously comes from the sun and moon together. A year comes from the sun appearing in the same constellation again. And then because of the fact that the sun goes around, moon goes around the earth in 29 days and not 30 days or something, 29 days, 12 full moons essentially will give you 354 days. And which means that there will be an 11-day overflow. And therefore, in ancient Indian calendars, what we used to do is that every 2.5 years, you about get 30 days extra. So we would add an extra month that was called the intercalary month or Adhik Masa. And you had two of them in 1 year, in 5 years. And therefore, 5 years was defined as the original Yuga period in ancient Indian literature. And then you have 19-year eclipse cycles where eclipses occur in the same pattern every 19 years. Jupiter and Saturn meet in the same constellation every 60 years. And this is, for example, been used by Sumerians and so on. And hundreds of years you get from precession. In fact, we don't appreciate, but the division, your compass uses 360 days precisely because approximately in 360 days, the sun comes back to the same position. So the protractor does not have 400 divisions; it has 360 divisions. But that comes because that comes originally from astronomy. People roughly said, okay, the sun moves 1 degree per day in the sky, and that is how we have 360 degrees on our compass, a protractor.
So that means, sir, sorry to
Um,
interfere, this concept of
yes,
protractor actually came from the concept of astronomy.
yes,
Okay.
that is a
Okay.
360. It's an odd number. It would have probably been
360.
easier to define 400 degrees on a circle or something.
Okay. That means whatever the geometrical drawings that we do in our school days using the protractor, this is basically the concept emerges from astronomy, which is later
That's
used
right.
in geometry. Okay.
That's
Okay.
right.
Thank you.
That's
Yeah.
right. Okay. So, Bob, but what I told you just now in a little while is something that it took human beings centuries to figure out. And the cultures had to mature to a certain level in order to figure out various pieces of knowledge. So, astronomy can be divided into four different steps. There is early astronomy, settlement astronomy, and astronomy of civilization, and technology based astronomy. We'll look at each of these things. If you just look out of your window and take a photograph of the sun, say on the first of every month, you will get a pattern like this. And because the sun will rise to the north of east in summer solstice, to the south of east in winter solstice, and it will keep on doing this cycle over the period of 1 year. And that is something that people notice very early because when the sun is roughly over here and coming from south, you get your monsoon. So even early cultures begin to appreciate this. They realize that the sun is the source of warmth and light and everything. The rains, the sun, the sky, etc., are crucial life givers. They realize that sky becomes the abode of the gods because that is where the heavens are. And arrival of the first art comes by about 35,000. The earliest rock art of astronomy is known to be 35,000 years old, but by 15,000 years BC, it is quite common. And people begin to settle down and look at this geometry because it is so much fun. So that is where, for example, this is a rock art in Kashmir in Likse, where you can see this idea of great superhuman controlling the skies. There are other interesting features. So, for example, there is a rock art like this which was found in Kashmir in the outskirts of Kashmir, where there is apparently a hunting scene with two suns, and obviously you can't have two sun, and the moon so close to the sun will be close to new moon. It cannot be as bright as the sun. So we suggested that this is probably a record of a supernova, and then if you look at the image seriously, you can actually go about looking for a supernova. So the idea is that the supernova should be between 2000 and 10,000 BC because that the rock art we know is at least 2000 BC and back. It should also be close to the path of the sun, which is called the ecliptic, and it should have been so bright that it would be visible during daytime for somebody to make an image like that. And because I can't show you my animation, I can't convince you, but there is only one supernova dated to 3000 BC, where if you put this picture, and if you put the location of the supernova, then this turns out to be Orion, this turns out to be Taurus, and Pleiades would be somewhere over here. So we think that this is the earliest sky chart of an eclipse dated to 3000, about 3000 BC, which is found in Kashmir. So people have noted extraordinary events. Then, if you look at settlement astronomy, people, once they're settled, they're talking of farming and so on, they now start becoming a little more serious about astronomy. So they start creating large scale structures. Now, large is mega and lithic means made of stone. So you get these early megalithic structures created at that time to understand the sky and so on. Some of these megalithic structures are for preserving the dead bodies and preventing, making sure that they are not eaten up by animals and so on, or dug up by animals and so on. But eventually, this also is used for astronomy to keep track of the movement of the sun and the moon. And we will see an example of them. Then constellations get noted, eclipses get noted, transient events such as comets, etc., get noted, and new myths are created, new ideas of what is the universe and why are we here and what is our place in it. The cosmological ideas about our relation to the sky begin to start forming. And megalithic, like I said, are large scale structures which are made with great diligence and care, and they are of astronomical use. There are about 2000 such structures in India itself. Most of them have not been studied. We looked at one of them. So there is a place called Baise near Udupi, where there is an interesting stone structure over here, and there are mounds, etc. So clearly, it's a very ancient site. If you look at the stones themselves are very large. So you can imagine this is a couple of meters tall. This stone is also a couple of meters tall, except that it is broken and fallen at the back. But these stones are not local to that ground. So these have been brought from quarries about 4 or 5 kilometers away with great care, huge stones weighing tons of kilograms being brought and put in a particular place. So clearly, it was not a random effort. It was not that it was a local stone or something. People have brought stones from a long distance to do that. If you look at the pattern in which the stones have been put, you would think that it is random. It looks completely random until you go back and simulate. When you simulate, you realize that the shadows of these stones don't go randomly. So the black color points that you have are all the shadows of the stones, and the red colored lines are the ones where the shadow of one stone meets another stone. So just to go back to previous picture, the shadow of this stone will meet this stone only at winter solstice and in the morning. In the evening, the shadow of this stone will meet this stone only at summer solstice. So just by seeing how the shadows move, we notice that there are about 9 alignments which will give you winter solstice and summer solstice by seeing how the shadows are there with respect to their partner stone. So anybody who is knowledgeable going there would see how the shadows of the partner stones behave, and you would be able to tell which time of the year it is. And this is the one at Bicep. There is another one at Nilaskal, which is also a very interesting astronomical observatory. So here we have actually an example of the same stone structure designed to give you calendrical purposes. And so these things typically get created during the megalithic period, second cultural period. Then there are tribal astronomy. So modern astronomy was more or less designed by Mesopotamia in 3000 BC, and everybody follows that constellation patterns. But tribal people do not have the same bias. They have their own ideas of what is sky and how the sky looks and what it is doing, etc. And so we studied astronomy of about 10 tribes in India, starting all the way from Warlis in western Maharashtra all the way up to Nicobar Islands. And we found that each tribe has its own astronomy. So, for example, Gonds believe that the Saptarshi, what we call Saptarshi, is essentially a bed where a constellation where there is a bed on which an old lady is sitting with these four legs of the bed, and there are these three people who are coming to steal the legs of the bed because the legs are made of precious metal. And therefore, by assumption, this lady is not allowed to sleep, because if she sleeps, these three thieves will come and steal the bed. And it so happened that until 1000 BC, this constellation never set in the sky in central India. So Gonds probably have an astronomical observation or a belief system that rose 1000 BC. And there are other reasons to believe that Gond tribals are actually more than have been settled there for more than 1000 BC. But their astronomical beliefs actually reconfirms that they remember an event that last occurred in 1000 BC. They also have a different way of looking at the sky. To them, Orion, that I told you earlier, is in fact a plow and a whole farming scene where they do all dehusking, they collect the harvest, they plow it, and so on. And there are bullocks and everything. And they can actually see all kinds of astronomical events, a farming event in the sky, how the gods are plowing the fields for their own need, and so on. The same constellation of Pleiades that I told you, if you look at it casually, you'll see about 6 or 7 stars. If you look a little carefully, you'll see about 20-25 stars. The same constellation. For Banjaras, it is a piece of jewelry. For Kolams or Pardis, it is a bunch of birds that are sort of flying around. For Korku, it is a minced meat. The Korkus are essentially meat eaters, and to them, this is the minced meat prepared by God for themselves. To Gonds, it is a bunch of stones thrown at birds because the birds are trying to eat up their product. To Varli, it is a drum or a light, and this drum is used for festive seasons. And so they can imagine a whole festival occurring around Taurus, Orion, and Pleiades. To the people of Nicobar, it is either the king or a group of elders who is looking from the top, giving them their blessing for their lives. To Pardis, they are two jungle babbers that are sitting there waiting to eat their food. And in conventional Indian mythology, they are the seven sisters. So they are called Saptarshi. They are called, anyway, they are called seven sisters. I've forgotten the name of it. So even from the whole sky, there are some the red color constellations are constellations which are seen by most several tribes, and there are some which are seen only by the oldest tribes. So, for example, for Pegasus and Leo, only Gonds have a belief system, but for many other constellations, they have other several tribes have belief systems. Then coming to Rigved itself, Rigved says that amongst the astronomy is the like the jewel on the head of a peacock. Um, s- Astronomy is the jewel of the Vedanta literature. Rigvedic astronomy has two parts. There is this Samhita itself, the text of Rigved itself, and then there is the Vedanga Jyotisha, which actually is the where explicit calculations about calendar etc. are given. And Tirak has analyzed the contents of the Rigved Samhita itself, and they call it Orion. He has published in a book called Orion because he thinks Orion is central to the astronomy of Rigved, and he has several very good reasons to do that. Rigved itself, for example, even has poetry about who we are, where we are. There's a very famous Rigved slok called Nasadiya Sukta, which says that at first there was neither being nor not being, there was neither air nor sky beyond. And then the poet keeps on speculating what was wrapping the world, where was it, etc. And then he says, the one who breathed it without the breath by his own impulse. Other than that, there was nothing else at all. And it is through this breath that the Great One gives birth to the universe. And then the poet says how he created the universe and all that. And then he speculates, saying as to who can tell us authentically, who really knows, who can tell us about it. And he says, when was it born? When was the creation? We really do not know the details. And he says, even gods won't be able to tell you because the gods were born after the this great event of creation of the universe. And then they speculate that maybe the one who created the world himself, surely, and he who surveys the greatest, highest heaven, the Brahman himself, he will know. And then the poets doubt that maybe even he doesn't know. And this Nasadiya Sukta actually forms the foundation of a lot of philosophical ideas which will be explored in later Sanskrit literature. So the first speculations of our place in the universe and the universe itself start coming by this period. The basic idea of Vedang Jyotish is to calculate for time being, they calculate, define the duration of the year to be 354 days and add the idea of a Dik Mas. Then for civil purposes, they say, okay, let us just define a 30-day month, 360 days, and then 5 days you either use it as a gap. Variety of ideas are given, including intercalary month if you to synchronize the solar and lunar calendars. Tirak in his book says that during the Rigvedic period, the equinox was in Taurus, or was in Orion, I beg your pardon. It was on in Orion, and then he talks about how in Orion, apart from Orion constellation for equinox, he also says that there are so many descriptions about the lifestyle in Rigvedic time that it seems that they were living much farther north of India rather than in India itself. And he talks about the fact that the sun is mentioned only thrice in Rigved, while Usha, the early morning, the dawn, is mentioned some 120 times or something. So clearly, to them, dawn was an independent goddess compared to the sun, and sun was not really a very important deity. It was Ushas, the dawn that was running the skies and so on. And there are several such other indications, all suggesting that Rigved was originally composed somewhere around 4000 BC, because that is when we have vernal equinox in Orion. And the description suggests that it was in the north of far much more like in Central Asia that they lived at that time. And so we looked at, so there is an interesting reference to a eclipse in Rigved, book 5, verse 14, 6 to 9, where Rishi Atri is called upon to dispel the doom of an eclipse that has happened. And then Indra himself is unable to help um, get the sun out of this magical spell of a demon called Swarbhanu. And they eventually approach Atri because the moon can't succeed. And if it is an eclipse, obviously moon would be the one that is causing the eclipse. They wouldn't know that, but they won't see Indra in the moon in the sky. So they had to ask Atri to help, and after some time, after some effort, in the fourth effort, eventually Atri succeeds in releasing the sun from the eclipse, the grip of the Swarbhanu. And they they very clearly say that the eclipse happened 3 days before the autumn equinox, and it happened. So it happened 3 days before autumn equinox, and if you assume that the eclipse was seen somewhere around 4000 BC, you actually end up with only one eclipse that occurs. So we look for all eclipses around 4000 to 2000 BC, and there's only one eclipse dated to October 23rd, 3811, which seems to describe, which is visible in Asia and which was a total solar eclipse. And if you plot it in the sky, you realize that it passes right through Central Asia and it does not pass through India. There are earlier eclipses of 4200 BC, etc., but then the sun is not in Orion as in at equinox. So clearly, there is even outright astronomical observation in Rigved which suggests that Rigveda was probably conceived in Central Asia. It was probably written down in the subcontinent, but the original ideas that they carried were from their life in Central Asia. Then you come across astronomy of civilization. Astronomy of civilization is there's a Harappan civilization. At this stage, you start speculating about our place in the universe. They start becoming more formal with mathematics. A lot of old ideas get reinterpreted and so on. And at this stage, you see a mixture of religious ideas and so on, all getting mixed up into mathematical observatory. So, for example, Dholavira is one of the Harappan civilization cities in the Run of Kutch. It is exactly a Tropic of Cancer. It is in Gujarat. And they have an interesting town. They have an interesting place called Bailey, which is to the left of their great town. And there, if you look at some structures that are really odd, and we have simulated and shown that these were probably designed for calendrical purposes. In other words, they have a hut which is of odd shape, and at 2 meters from the top, if you made a hole, then the sunrise point would travel like this over the period of 1 year. And so you would see the at vernal equinox or at the sorry, at summer solstice you'll see the sun shadow over here. At winter solstice you would see it over here, and just putting a plank and seeing the direction of movement of the sun, you would be able to tell. You'll be able to make a full calendar. There is another, and this is what the simulation shows, that at summer solstice the shadow would move right across the bottom. At winter solstice it would move right across the top, and it would in fact go and make this jump from here to here to confirm that it is winter solstice. So we think they have observatories. Then in India, we get Janapadas who have their coins by about 700 BC. These are punchmark coins from about 700 BC. They are typically a few millimeters in size. Initially, they have a lot of gold and silver. Eventually, as the civilization becomes poor, they add more lead and stuff like that. But on these, there are punch marks. So you can imagine this whole structure is a couple of millimeters in size. And then they have additional sun and so on markings and all that. And some of them look like astronomical. So there are a whole bunch of them which seem to suggest that there is something in the sky because there is an animal and there is something on the top of the sky. And typically, when you are top of the sky, they tend to have a pattern of dots, 6 or 7 dots, which would fit Pleiades like that. So if this could easily be Moon and Pleiades, and this happens every 18 and a half years with Saros cycle. And that is why we think that all these are indication are all markings of days or the year in which this kind of conjunction happened. The moon is here and Pleiades are over here. And we think there are other signs also. So, for example, this seems to be the sun. There's this famous belief that the earth is looked after by elephant who stands on the um, tortoise and so on. So there are markings like that. These probably are markings of comet observations or even Pleiades observation over here. And you could see different things in the sky. So we believe that punchmark coins also used astronomical data for the making. This is what it looks like. This is where I told you all the details images can be seen. Then even Ajanta and Ellora have astronomical orientation, even though Ajanta is in the form of a semicircle, it still has interesting astronomical orientation. Some caves directions have been slightly changed to fit in the astronomical events. Then there are philosophical ideas. I think I'm running short of time, so I'm going to skip that part of the story. But there are stories in Brihadaranyaka Upanishad which tells you about what the universe consists of. So there are
No, sir,
speculations.
if you want
Temples in
just
India.
cite some examples, it is okay. We are all listening to this wonderful lecture.
Yeah, so originally, yeah, so there is somebody called Gargi. She asks Brahma, Yagnavalkya as to what is the earth. So he says the earth is surrounded by water. Water is surrounded by air. Air is surrounded by sky. Sky is surrounded by the world of Gandharvas. The world of Gandharvas or planets is surrounded by the sun. Then comes the world of moon. Then comes the world of nakshatras or constellations. And then there's world of the complete abstract worlds of Devas, Indras, Prajapati, and Brahman. And when Gargi asks him what is beyond the world of Brahman, he just tells her to shut up. And if you think about it, except for the moon being outer to the sun, the sequencing seems to be pretty good. And so there are ideas which seem to mix current whatever was available as geographical knowledge into philosophical ideas and so on. Temples in India are a representation of gods in heaven. So temples in India are not originally there in Rigveda or early Vedic religion. It is in 500 BC that Buddhism comes to India, and when Buddha passes away, every all his followers want to have a part of him. So his hair are distributed to various places, and the worshippers make monuments that we call stupas, where at the base of the stupa is this hair of Buddha, and then the entire and the stupa is made. And very soon as around 500 BC, the Hindus start realizing that this stupas are very useful in gathering your flock. People come there, pay their homages, etc., etc. And so in India, Hindu temples come as sort of follow up of that, and temples in India are representation of the heavens in the sky, and it is in some sense a borrowed idea from Buddhism. But if you look at the center centrum where the god himself sits, the center of the temple is Brahman. And then there are various constellations and various gods cover different corners of the temple. But this temple structure, the Sankra where the idol itself is put, has a fairly elaborate pattern and it can be only in even numbers and stuff like that. One of the finest Hindu temples is not in India, it is in Cambodia. It is called Angkor Wat. And just to give you an idea, it is 1 kilometer wide compared and is 700 meters long. Say 1 kilometer by 700 meters. And the number of steps here are exactly some 1056, I think, as per the number of verses and so on. And in the center of it sits what they called a replica of Mount Kailasa, and various Indian philosophical structures are there. So there is the world of humans covered by the world of water. And this is a 12th century temple. And it is so sophisticated, for example, that in summer months, the amount of water will go down, and in winter months, in monsoon, the water will rise. And if you let it happen natural course, then what happens is this island would become unstable. So they have taken elaborate care to make sure that even if the water level goes up and down, the temple itself will not be damaged in any way by isolating and all that. It's a phenomenal piece of temple architecture. If you want to see a good Hindu temple, you should go to Angkor Wat in Cambodia. Then there are other things that the calendrical thing that I'm going to skip. I'm going to come straight here. So if you look at Rigved, for example, it has references from of astronomy from 6000 BC. So vernal equinox is everything from Orion all the way to Pleiades, and the movement of the vernal equinox is noted, and Tilak has pointed this out. Then Brihat Samhita has memory of what is called Rohini Shakatpet, where Saturn, Mars actually goes through Taurus, and that comes to about 5200 BC. Yajur Ved remembers that the vernal equinox is Kritika, which is 2350 BC. Kritika is Pleiades. I was trying to remember. Then um, Maitreya Aranyak, or the corresponding Upanishad, is gives the visibility of Alpha, Epsilon, Leo at the time of Kurukshetra, and that comes to between 1980 or 1600 BC. Yajurved Jyotisha gives you the summer solstice in Ashlesha, which is 1370 BC. These are all BC, remember that. Even the last date of Parashara Samhita is 11 to 1300 BC. Is essentially means 3000 years, 3000 to 3300 years ago. And so we have various dates which suggest that the astronomical literature is you can date some of this astronomical literature, which gives you dates from 6000 BC all the way to 1000 BC. Then there is modern astronomy. So, for example, if you go to fishermen in Mumbai and say you want to travel to the Gulf, they don't use GPS systems and they don't use electronic devices. For every port, they have a plan like this, which says that if you want to go to, say, Dubai, then you follow this star pattern every in a specific day of the year for so many days in one direction. Then you will reach the next port, look at the next port, look at their charts, and follow, say, this pattern for another 2 days, and so on. And they navigate entirely by the constellations. In ninth century, in fact, Chola kings even tried to redefine the constellations depending on what they saw as the sky. So there, the Orion becomes now the Nataraja, and so on. And Lepus becomes the demon underneath. Then Canis Major becomes the dog, and so on. So various astronomical attempts are made. There is a very famous Kepler supernova 1604, and there is one tile of a in one of the Mughal palaces in Kashmir, where tiles for Sagittarius that were made before 1604, the tail of the this animal is tail of tiger is normal, but in so the one that was made in 1604 actually has the tail on fire, and that is where the supernova 1604 happened. So there are drawings of astronomical events that go back to that period. Uh, then there is specialization. People now start working on mathematics in great detail, and we have what is called Siddhantic period in India, starting with 500 AD, where Aryabhatta for the first time notes down all the astronomical knowledge of that time, and it's called Aryabhatti, and that is where the modern astronomy begins. So he defines the sine functions, he defines series, and so on. And so on. The original origin of Indian mathematics actually is in Rigved, in the sense that in Rigved they may have havans through which the gods are to be pleased. Now all the gods cannot have havan vedi that looks identical. So some had to have semicircular, some had to have square, some had to have rectangular, and all that. And yet the area could not be different, because otherwise the god with a smaller pyre would get very upset. So the original mathematics of India begins by trying to get Vedis of different shapes but of the same surface area. That gives series, arithmetical series and value of pi and so on. But by Siddhantic period, people are now preoccupied with calculating the planetary locations and all that. And the first algorithms about how to calculate various astronomical entities comes in. Basics of trigonometry come into play, and so on. And mathematical formulation by then reaches fairly sophisticated level. So we actually have formal sine function. We have ways in which to define the value of the sine functions for any angle theta and so on. And eclipses are now fully recognized as being the shadow of the moon on Earth or the Earth on moon, depending on whether it is solar or lunar eclipse. And planetary locations are available. In some cases, astral charts are also made. In Interestingly, Varamira in 505 AD writes in Bruhat Samhita as to who can be an astronomer. And they say astronomer is somebody who can do time division, who can calculate planetary calendars, who can calculate terrestrial calendar, who understands solstices and can calculate them, who can calculate the eclipses. He can calculate the sun's daily and annual motion, the latitude and longitude of a place with Ujjain as the zero latitude, and understand nakshatra and zodiac. And interestingly, teach it to a smart student. It is interesting that astrology, knowledge of astrology, is not a part of the syllabus. Astrology is not an Indian concept at all. It comes from Yavanas, from the Greeks, around the time of Varamira. But no honorable astronomer of that period would talk about astrology, because it is not, astronomy was not supposed to be, it was supposed to be just a pure science. Then we have, of course, by the time you come to 6th, 17th, 18th century, we have Jantar Mantar, and Jantar Mantar is completely overtaken by telescopes. This is radio telescope at GMRT. So by that time, we have modern astronomy, telescopes coming, invention of other instruments coming. We realize multi-wavelength nature of astronomy. We start putting our physics into astronomy and so on. And we call it what we call today's astronomy and astrophysics. And so, just to summarize, we began with initial phase of astronomy, where just the sun's locations are the one that counts, to megalithic astronomy, where stone structures are made to identify direction of the sun's motion, and then the astronomy of civilization, which has its own complexities, and last is the modern technology-driven astronomy. Interestingly, if you sort of take various communities and their astronomies and write down the period since they were settled, you can then quantify how much astronomy they know. Did they know constellations? Did they have name for direction? Did they know constellations? Did they use astronomy in daily life, etc.? And eventually come out with a cumulative score about how much astronomy they knew. So Gone's astronomical knowledge was 27.5 compared to early UK, which was 50, and today, of course, would be 100. Based on this, you can then draw a graph of times in settlement and the level of astronomical sophistication, and you get a beautiful line fit from rural to urban, tribal to urban civilizations, with a chi-square of 0.96. Clearly, as the civilization settles, it takes more and more interest in astronomy, comes out with more and more new concepts and so on, and ideas and philosophies. And therefore, if you know how old a civilization is, you should be able to define how sophisticated their astronomy is. And if you know how sophisticated an astronomy of a culture is, you can define how long they have been settled. So the bottom line is, for example, for India, if you say the initial astronomy would go from 50,000 to 5,000 BC, settlement astronomy would go from 5,000 BC to 2,500 BC for Harappans, who then disappear with all their knowledge and is not carried forward. While for Vedic literature, etc., it's about 1500 BC for onwards for later Vedic period. Astronomy of civilization, again, Harappan civilization would have had fairly sophisticated astronomy, but their knowledge system is not left behind. So we believe it. So for civilization, it would be more like 1500 BC to 500 BC from Sanskrit literature and so on. And technology-based astronomy comes from 500 BC, when Aryabhatta writes down his Aryabhatta. So the bottom line is, astronomy can give you a good map of intellectual growth of a civilization, and you can use astronomy as a probe, and the distinct stages are very clearly seen. And therefore, astronomy is an excellent window to the past. Thank you very much. I have completed my lecture, and if you have any questions,
Yes, sir.
you
Yeah.
can ask.
Yeah, absolutely. Sir, we have one question coming up from Debolina. Although it is not related to astronomy, however, you are the right person to answer. She is asking that, sir, can you brief about Michelson Morley experiment? As a very recent way, we have an experiment using Michelson Morley interferometer to measure the wavelength of laser. What is the real
Correct.
motive to do this experiment?
So Michelson Morley experiment. was the is the only experiment that failed to give the result it was expected to, and yet won a Nobel Prize because fundamentally it altered our understanding of physics. So the question is, you have Newton, who says that if you throw something, it will go with a certain velocity, but if you run and then throw it, the velocity will be higher. That is why cricket bowlers, for example, run and then throw the ball because they get more speed out of it, and pace bowlers run more and spin bowlers run less, etc. The idea is the same, that if you run and throw the ball, it has the velocity of the ball will be what your arm can give plus your own running speed can give. On the other hand, Maxwell says that the velocity of light cannot be changed. It is about 300,000 kilometers per second, and it is a universal entity, whatever you do. So the question that came up in early 19th century was that if you have a torch, and if you're standing and shining a torch, or if you're running and shining a torch, will the velocities of light be different? Maxwell said no, and Einstein and Newton said yes. And obviously, the Earth's human motion is too weak or too small for that time's technology. But the idea that the Earth itself is going around the sun was used. So if Earth was going in the direction of the ether, the universal medium that was supposed to cover the Earth, then the velocity in one direction would be higher than the velocity in the other direction. So if you keep your device measuring velocity measuring device in say east-west direction, you would get one velocity. If you keep it in north-south direction, you would get another velocity. What Michelson Morley experiment does is to improve in the sensitivity of these kind of abilities. So it takes a beam of light and splits it into two, and then it is reflected orthogonally from two units, and the light comes and merges again. Now, if the light has traveled exactly the same distance in both the orthogonal directions, then you will get a constructive interference. If one of them has moved slightly, then you will get a destructive interference. So, if the light photon that is left this splitting mirror, if it goes in the forward direction fast and comes back fast, then you will get a different interference pattern than if they were both on the same velocity. And Michelson Morley tried to point out that if you put the instrument east-west, then the light in the east-west direction moves faster compared to north-south direction, and it failed. And it showed that the universe velocity of light remains the same irrespective of the direction, irrespective of the motion of the Earth. And therefore, it fundamentally showed that Newton's theories needed to be modified because Maxwell was right. And the idea of addition of velocities by running, etc., is good for cricket playing, but it is not a universe. It is not true of universe, especially when you're talking of velocities like velocity of light. So that was the basic reason for Michelson Morley, and its failure would eventually lead to Einstein's theory of relativity and so on, and it fundamentally changed the physics completely. But that was Michelson Morley.
Thank you. Thank you very much. It was a very lucid and an easy explanation. Second question coming from Raghav Manchanda. Sir, how the radio telescope works?
So, but you have a television at home, and if you remember, you have these large antennas. What radio telescopes do is that they collect light at a much longer wavelength. So, optical wavelengths are typically a few nanometers, but you can have electromagnetic radiations which have 1 meter wavelength or even longer. And you can, of course, have very, very short wavelengths, which we call gamma rays. The longer the wavelength, the lesser the energy content. It also means that the longer the wavelength, the more easily it will go over obstructions and so on. So, radio astronomy allows you to see much deeper than, say, gamma ray astronomy or X-ray astronomy. So what radio telescope does is to collect this light that has a wavelength of a few meters, a few tens of meters, and so on. And because the wavelength is very large, the mirror equivalent for a radio telescope is this disk. So if you look at television, if you try to get a television disk, typically it tends to be about a meter in size because telecommunication wavelengths are something like that. If you look at, for example, if you think about it, all mobile phones have roughly the same length. And that is because the wavelength at which mobile phones work have the wavelength that is typical of that size of the mobile phone. And therefore, mobile phones can receive the signal. You can't make a very small mobile phone, or you can't make a very, if you will, you can make it larger, but you can't make it very small because then it won't be resonate with the signal wavelength of the light that is radio waves that is falling on it. On the other hand, because these radio telescopes work on centimeter and meter wavelength light, they need disks which are typically larger. So GMRT, for example, each disk that I showed you the picture is 40 meters in diameter. And so it collects light from at very long wavelengths. It reflects it on that curved surface. And right in the center at the top, there is a detector which detects the amount of light of that wavelength that has been received and then converts it into astronomical knowledge. So it looks at various points in the sky, finds out how much intensity is there, and then on a piece of paper or a piece of computer screen, you can find or you can plot the intensity of light that are coming from the various part of the sky, and that is how you get images. That's how radio telescopes work.
Okay, thank you, sir. Quite a lot questions coming up quickly. I will take it. First of all, somebody called Mazin the Lab is asking this question: why we represent light as ray or beam?
The reason why we represent light as ray or beam simply because light has rectilinear propagation. It propagates in a straight line. So if you have a light at a source, if you have a light at one point, and if you want to see how it will go at the other point, especially if you, I mean, in principle, of course, any ordinary light source will emit light in 360 degrees. But suppose if I have a light source and if I put a pinhole on that, the light will travel along that pinhole light source direction. So light has this rectilinear motion, and therefore it is most useful to draw it as a ray. Unlike sound wave, for example, it will not travel as a wave; it will dissipate. But light travels as a straight line, especially when you make it laser, it can travel several hundred kilometers just as one single ray. And that's why it is more convenient to represent it as a ray.
Right, thank you. Sir, Debolina is telling, thank you, sir, for explaining in such a easy way.
Thank you very
The
much.
Michelson Morley. Okay, we have another question from Karan Nalawat. He is asking, how did ancient Indians were able to do astronomy without instruments?
Oh, astronomy, instrumental astronomy, instrument. So my whole lecture was to show you how they developed various instruments as their understanding of astronomy grew. So originally they were just looking at the sky. Then they started realizing, like, look, sky has patterns. There is a repeated pattern, so they made constellations. Because monsoon was related to a particular pattern in the sky. So, for example, the Egyptian pyramids are probably designed like Orion, because whenever Orion came in the sky in the night, they had flooding in Nile, and somehow they thought the two were related. We know that equinox is the one that brings equinox is somewhere in June, and typically monsoon in India strikes in June. So then they would realize the relation between the sky and the seasons and so on. So they would want to keep better track of it, and that is how the megaliths come in. And then as time goes, they make it more and more sophisticated.
Absolutely.
Then it's a
Thank you,
question of
sir. Yeah,
what you want to know and making instruments for it.
yes.
Yes.
He is asking, Karan is asking another question. How accurate are Indian calendars as compared to Gregorian calendar?
So Indian calendars are lunar calendars. Okay. We do not recognize the solar months. So we have lunar months 20. Unfortunately, the moon goes from full moon to full moon every 29 and a half days. So there are some months which will have 30 days. There are some months which will have 29 days, and so you have this tithis which are missing and stuff like that. In that sense, it is a fairly inconvenient calendar to use, because back calculations would be impossible, because you have to know exactly when the 29-day month occurred and when 29 and a half day month occurred. Compared to that, the Gregorian calendar and Julian calendars are solar calendars. They don't bother about the moon at all or the phase of the moon. And so it is more linear, more easier compared to lunar calendar. On the other hand, they stick with this idea of 12 months, which comes from lunar calendar, because 12 full moons will roughly make the sun come back to the same location. So they still stick with 12 months in a year. But because they only now go by the location, 360 degrees, like I said, is the protractor, and 1 degree per day. So they would only look at the movement of the sun with respect to the zodiacal sign and define the day. So it was more accurate, more stable compared to what the lunar calendar was.
Right. Thank you, sir. Sir, the same person who asked you the question as light, as ray or beam, is asking that if light moves in straight line, so can we without any hesitation represent it ray or beam?
Um, So there is a problem with light, in the sense that normally, if you're doing working with lenses, etc., using ray is perfectly fine. And in fact, it's quite amusing, quite confusing in some sense, that if you take a bulb and if you put one light, one cardboard piece, one hole in it, light will behave like a ray. But if you put two holes in it, light behaves slightly differently. And so light has this dual properties of being wave and ray. Wave and well, it is called wave and a packet of energy, a photon. So photon has wavelength and frequency and so on. So light has to be, depending on which situation you're talking about, you will either call it a ray or a wave. And light behaves differently inside. So it is not 100% true to say that we can use light always as a ray, because it does show interference patterns like sound does, etc., under specialized condition.
Right.
The workaround to it is to say that light is a packet of energy we call photon. The energy in it is dependent on the frequency and wavelength, and because it has a certain frequency and wavelength, it obviously has this pattern of a wave, and therefore there is a certain degree of uncertainty in its location, plus a certain degree of uncertainty in its behavior, which will at times also show it up as interference patterns, which are classical of waves. So light obeys both wave properties as well as uh, ray
Particle.
property.
Right. So I think, sir, you are referring to the wave particle duality and then the uncertainty
Yes, yes,
principle as on. Okay.
correct.
There are two questions coming up from Raghav Manchanda. One is that what is gravitational wave astronomy and what is gamma ray burst?
Okay. So we know, for example, that when you make a charged particle move, it produces electromagnetic. We have seen electromagnets, and we have done, I'm sure, experiments. And the very fact that light bulbs work, etc., is because if you take a charged particle and make it slow down, it will the difference in energy will be released as electromagnetic radiation or light. It turns out that what is true of light is also true of solid objects. So, for example, when a solid object moves, also it gives out equivalent of electromagnetic radiation that we call gravitational wave. Except that if you remember your electromagnetism, then the force is given as Q1 Q2 by R square, while in gravity it is given as G into M1 M2 by R square. So M1 M2 by R square or Q1 Q2 by R square is the same, but the value of capital G is 10 raised to minus 26, while the same constant in electromagnetism has a value of 1. So the gravitational waves are 26 orders of magnitude weaker. And therefore, when you and I move, we cannot sense the gravitational waves that we release. But when astronomical objects of several solar masses move, they create a gravitational disturbance in the universe, which is visible. And gravitational waves, therefore, are waves that are produced by any movement of any gravitating object, which disturbs the fabric of space-time, just as electromagnetic radiation disturbs the electromagnetic environment of the universe. And what was the second part of the question?
Second part was
There
what
were two
is
parts to the
gamma?
question.
Yeah, gamma ray burst.
Yeah, gamma rays are simply electromagnetic radiations of very high energy. And when two gravitating objects move, they produce gravitational waves. Especially when they collide, they produce gravitational waves, and therefore those collisions are the most energetic, and we can see them for long distances. That is how gravitational waves are detected, when two neutron stars or two black holes merge and so on. Gamma ray bursts are essentially burst of energy that comes out when there is a death of a star, or when two very heavy stars go and bang into each other. Gamma rays are, of course, light photons of very high energy, and you get a burst of them from some region in the sky. We believe that many of them are of mergers of very large astronomical objects, which merge into each other, or where there is an exploding star or something, which releases a whole burst of gamma rays in a matter of few seconds. Okay,
Thank you, sir. Sir, one interesting question coming. I'm sorry, taking up a little bit of time of yours.
not a time, not a problem.
What do astronomers actually do? Is it all about observing sky?
What astronomers? Okay, so astronomers actually have two different groups. One is called astronomers and the other is called astrophysicists. Well, there is also astrochemists and astrobiologists, but so theoreticians and experimentalists. What what um what observational astronomers do? You can't do experiments in astronomy. You can only observe. What you do in observational astronomy is to create telescopes, ever increasingly better telescopes or more intelligent telescopes, and so on, to look at various regions of the sky. And so they are essentially doing the observing part of the story to tell you what is happening where with as great a precision in space and time as possible. As small an object as possible, they want to see. And if there are movements within that objects on time scales of, say, milliseconds or microseconds, they want to know it. So astronomers essentially make, and of course the wavelengths, whether it is happening in radio to gamma rays or optical light, etc. So they use different wavelengths to study. They use different technologies to get as small a region as possible. Some people also like to look at a wider region of the sky. So they define the region of the sky they want to study in the wavelength in which they want to study, and with as fine a time resolution as they want to study. So they make instruments that optimize these three depending on the problem they're interested in. Astrophysicists, on the other end, use our knowledge of physics as developed originally in the labs and then in cosmos, Kepler's laws, and a lot more than Kepler's laws. Still, we now know how stars burn and we know how stars die and we know how galaxies are formed. We know how the universe was born, all that. So they try to use that physics knowledge of theirs to try and understand how what astronomers have observed. And in some cases, they of course make predictions saying like, look, this is what should be happening, and they ask astronomers to go and look at those things. So astrophysics is the one that helps us lay theoretical foundations to understand how the universe. So, for example, astrochemists look at chemical reactions happening in large clouds in the universe. Astrobiologists worry about whether other planets can have life, what is the environment needed for life, and so on. So, astrobiologists, astrochemists, astrophysicists use our current knowledge on Earth to try and understand more of the cosmos. Astronomers are the ones who observe with as much precision, as much of time resolution, and the wavelength of their choice to any particular problem that interests them.
Right, sir. A lot of questions coming up. I will be very quick. I know you will be tired after an hour's lecture. Sir,
No, that's okay.
Somnath Safi is asking, I think you can see the, now you can see the, it is
Yes.
on the audio screen. What technology and analysis is used to identify angle of inclination of planet on another galaxy?
Oh, you don't measure the angle of inclination, etc., because another galaxy, at the most, even Andromeda galaxy, is less than an arc second, a few arc minutes wide. One arc minute is 1 upon 3600 of a, 1 arc second is 1 upon 3600 of a degree. So the sizes are very small. So for stars at very great distances, you don't really measure their inclinations and stuff like that. You measure the inclination of the galaxy as a whole, and then you worry about relative location of various stars within that galaxy, taking the image of the galaxy. And also, galaxies move very, very slowly. So, our own galaxy, for example, takes 250 million years to go around. So, in a lifetime, or say 2 or 3 lifetimes, or 200-300 years, the stars will not move in that galaxy at all. You require thousands of years for any visible change in the design of the galaxy to look, and generally, it will be rotation. What you can measure is that if the stars are moving towards you or away from you, the light that comes from them varies slightly, that the so-called redshift or blue shift, and that you can measure. But that again, you don't do an angular study. You only measure the velocity with which they are moving. You do not do within an external galaxy. You don't do angular measurements of location of stars.
Thank you, sir. Sir, Sonu is asking this question. Is it possible to pursue astronomy after MSc Mathematics?
Answer would be yes. The answer would very much be yes. There are two things that, so for example, our entire foundation of our modern knowledge, we invented mathematics as a language originally for trading and then for the fun of a language. Now it turns out that nature itself speaks in the language of mathematics. So mathematics is crucial to almost everything that is done in the happens in the universe. So if you have done MSc mathematics, you can either read up a bit of astronomy or astrophysics, and then you can apply for a PhD position in any university or any good research institution and appear for their interview. So they will ask you basic. The problem will not be with your knowledge of astronomy. The problem is if you've done MSc Maths, your physics foundations will be weak. And astronomy is a mixture of mathematics and physics. So if you can catch up on your physics a little before you go for interviews, much of that physics is actually mathematical. But anyway, you have to know the conditions under which mathematics is used in physics. And so if you can sort of brush up on your physics as a typical BSc student would know, then you can definitely apply for PhD in astronomy in any of the good institutions or even universities, appear for an interview and make it. There is, frankly speaking, mathematicians would do well in astronomy, but
Yeah.
sometimes they would lack the basic knowledge of foundation. So if you can clear up your foundations of basic physics, then you really can do astronomy for sure.
Right. Sir, Mazin the lab is asking, sir, what if photons have volume? Then what will happen to the phenomena done by it?
So photons have frequency and wavelength. Now, in some sense, frequency is the amplitude of the wave, and frequency is the number of times it goes up and down within a fixed amount of time, and wavelength is essentially the amplitude of how much it will goes by the amount it goes up and down. And in that sense, you can actually call it a volume. And therefore, what happens is that within that volume, the location of photon is uncertain. You can never pinpoint the location of a photon with infinite accuracy, because eventually you will come across the size of the photon, and within that size you can't define, and that size itself is defined by the frequency and amplitude of the photon, or the energy of the photon. So those, yes, so light photon can be considered as a considered to have volume, and you can actually talk about interference between two photons of different similar wavelengths or different wavelengths, and you get all kinds of astronomy, okay, all kinds of physical processes.
So Chandan is asking, can you refer to some apps to explore night sky of your area?
Oh, there are plenty of night sky observations. I'll tell you which is my favorite. No, 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 no. So Stellarium, I think, has for computer, Stellarium is a very good one. Otherwise, Star Trek is another good software. Star Walk is a very good software. Both are free. Star Walk 2 for phones, and actually the advantage of Star Walk 2 is that as you turn your phone, it tells you what is the location in the sky. By GPS, it knows your location, and by angle, etc., it knows where you are. And therefore, if you point it to any region in the sky, it will tell you what are the constellations behind the telephone. If you're serious about astronomical constellation studies, etc., for your laptop, I would suggest you use Stellarium. Both are free softwares.
Stellarium and Star Trek. Okay. Raghav has got one question asking to you, sir. How scientists calculate the expansion rate of universe?
So there's a very peculiar phenomena that people have seen, that when they have looked at objects at different distances, they have found them to have different velocity. To give you another crude numerical example, you can assume that anything that is 1 meter, you find a very strange phenomenon in the universe, that something that is 1 meter from you is moving at 1 meter per second, something that is at 5 meters from you is moving at 5 meters per second, something that is 10 meters from you is moving at 10 meters per second. And the obvious question you can ask is, what was the situation 1 second ago? And everybody was at the same place at the same time 1 second ago. In the scale of the universe, of course, that 1 second is 13.7 billion years. But essentially, you look at the rate at which everybody is running away from everybody else and try and guess the past. And it turns out that 13.7 billion years ago, everybody was at the same time at the same place. And how do you measure the velocity is because of what is called redshift. As an object that is if you have ever sort of waited on a railway station, seen an engine coming in, then as the train engine comes in and if it whistles, the sound will appear more shrill as the engine is coming towards you, and it will appear more will appear to have more bass as it goes away from you. So it will have more treble as it comes towards you, and more bass as you go away from you. Exactly the same thing happens to light. Any light source that is coming from you will appear to have higher frequency and therefore will appear blue. any object that is going away from you will have the light that is shifted to red, and therefore it will have a red shift. It will have a higher pass, and therefore it will appear like red shift. And these red shifts turn out to be an accurate measure of velocity with respect to you. And that has been used to determine the expansion or rate of the universe.
Thank you. Somnath sir, Somnath is telling thank you, Mayank sir, for such a
My pleasure.
fruitful lecture. This one
Thank
question,
you.
I know, sir, it will take time, but I think with your expertise, you can just explain it simply. Raghav is asking, what is black hole thermodynamics?
So thermodynamics is the thermal property of any object. Now, black holes themselves, we don't really fully understand, but we definitely know that they are objects with such great density that not even light will escape from it. Now, you can imagine from the sun, the escape velocity is 400 kilometers per second. From Earth, it is 11 kilometers per second, and so on. And black hole is an object where the escape velocity is more than velocity of light. Therefore, even light will not escape. But even on Earth, for example, if you want to fire a rocket from the ground, it is 11 kilometers per second. If you want to fly a rocket from, say, 100 kilometers up, the escape velocity will be slightly less. So from the black hole itself, the further away you go from black hole, the escape velocity becomes less and less and less until you reach an edge point where the escape velocity is equal to velocity of light, and from beyond that you will get light. So you will see light coming out from regions just outside the black hole. So the question is, what is the surface of a black hole? And surface of a black hole, it is called various event horizon, Eddington radius, various names are there. But that surface is a surface. And so you can talk about thermodynamics of that surface. Will it have temperature? If it has temperature, will it have kinetic energy? Will it look like Planck curve? What happens? We know that radiation under such intense environment behaves differently. So you have a gap, whether particles will have gas laws or not. All kinds of questions of that you ask in classical thermodynamics. You can ask about the surface of a black hole from where the velocity of light is, escape velocity is less than velocity of light, and therefore light can escape. And that is referred to as the thermodynamics of a black hole, the study of the surface of a black
Sir, there is one question is that, sir, is the expanding universe like impurities moving water flowing in pipe?
hole. No, no. Expanding universe is a very completely different entity. The universe was one point at one time 13.7 billion years ago. There was no space, there was no time, there was nothing. The universe creates its own space and time. It is like a cake that is sort of fluffing up. It is not a flow in the sense of a water moving or a fluid moving in a tube. It is a universe that is creating its own space and time and expanding within that. So it's a fundamentally different entity.
Right. Thank you for clarifying, sir. As we come to the end of our podcast, I have one question, one or two just questions, taking a little bit of time. Sir, you helped to initiate India's Astronomy Olympiad program. Now, how has
Correct.
that shaped the next generation of space scientists? If you can just tell us a little bit more.
Yeah, so I'm very happy to say that the idea of Astronomy Olympiad was not just to create astronomers, but even to create physicists in general. The idea was that every parent is uncertain whether their child, if he takes up pure science, the problem with pure science careers is that you have to be excellent. And therefore, every parent, you can be a mediocre doctor, you can be a mediocre engineer, you can't be a mediocre scientist. Then you become a technician. So every parent is worried whether their child has the mental required to be a professional scientist. So Astronomy Olympiad, like other Olympiads, give a platform for the students to test their understanding of the subject concerned. And I'm happy to say that I think more than half the Astronomy Olympiad students have gone on to become scientists in some field of physics, and the rest have gone into engineering. Very few have deviated completely away from science. Very few.
So, lastly, what I would like to ask you is that, given two areas of study, one, as you told that one, there are a lot of students who want to get into pure mathematics or purely
Correct.
mathematical or theoretical study. Another is the experimental science, and where you go and evidence. Now, obviously, there are students, their parents would say, don't go into pure maths because there is no career, etc., all those things. And there are few people who would like to go in pure maths or theoretical study, and a separate branch wants to go into experimental physics or something, get a steady job and earn money, and then do the rest, live the rest of the life. As you being so many years in TIFR, you have met many scientists, have traveled around the world. On a very honest note, sir, what would be your suggestion as far as India is concerned? What would be for people who are, or the students who are coming from a backward family, who really don't have their parents who can sponsor for a long time, and those who are coming from a rich family who really wants to go? How would they balance, and what would be your say, which area one should aspire and which area should go? Are there risks in going in pure studies? If they fail, then what to do after that? Can you give us a kind of an understanding in part of the career is concerned?
So, personally, I think career should depend partly on interest or largely on interest, and more importantly on commitment. Nobody is born a genius. Nobody, not even Einstein was a born genius. Okay, in fact, he was quite a dullard in the school. But he had the commitment. If you are willing to commit that you will study whatever subject you want to study, then there is, and commit is a very serious word. Commit means you will have to give up on parties, celebrations, festivals, etc. You have to be obsessed with the subject which you want to study. There is no alternative to that. If you are willing to commit that kind of your life to simply studying the working of nature or language or whatever you have it, then by all means go for science. But if you want to have your parties on the side, and if you want to have festivities on the side, and if you want to study only for exams, etc., don't even think of going for pure sciences, because you will not succeed. Science, any study at that level requires full time emotional and physical commitment to learning that subject. Nobody is a born genius. Everybody who became a genius did it through hard work, and there is no alternative to that hard work. If you are willing to put in that work and you're committing to say that, okay, I want to pursue knowledge and studies for the sake of studying knowledge, there is no stopping you. Whether you'll take mathematics or physics, etc., I think, should be left to the student himself. If you are willing to excel, there is no shortage of places. In the worst case, suppose if you do mathematics very well but struggle to find a job in pure maths, there are plenty of jobs in applied maths. These days, applied maths is the thing because computers are essentially applied maths. Mathematics is a universal language. From mathematics, you can go anywhere you want. Social sciences, physical sciences, art, music, literature, whatever you want. Mathematics is not a subject that is used by somebody else. Mathematics is a language, pure and simple. And when you write down the working of nature in mathematical language, it gives you insights which nothing else can give. So social science is also the same thing. If you write down the human behavior in a mathematical format, it gives you insight which nothing else can give. Whether it is archaeology, whether it is social sciences, whether it is human behavior, whether it is economics, etc. If you have a sound footing in mathematics, you can go to anywhere in the world, including astronomy. Um, but you require commitment. So first, you must be sure that you are willing to make the kind of commitment that a pursuit of pure science requires. If you're willing to do that, then which part of pure science you select is up to you. If you do mathematics, there was a time when mathematics you were either a pure mathematician or you were nowhere, or you became a teacher, etc. Now with computer science and related fields coming up, AI and all that, mathematics has become the foundation of most of our high level activities. So there are plenty of jobs, but you have to excel. You can, like I said, be a mediocre doctor, you can be a mediocre engineer, but you can't be a mediocre scientist. So you have to make sure that you're willing to commit to that kind of time and energy, and then there is really no stopping you. On the other end, if you want to have your social life and if you want to have fun in life, don't even think of going to pure sciences. Quietly become an engineer or a doctor or something like that. You'll probably earn more than what a pure scientist will, and have your fun. But at the end of the day, I would not do that for all the money in the world, because the job satisfaction that you get from pursuing science to learning something that nobody knew, before is a joy that is unmatchable. So, for example, people have been seeing that the moon is going around the sun, around the earth. But it took the genius of Newton to realize that the moon, in fact, is trying to fall on the earth. But like a projectile motion, it is missing the horizon and therefore it is going around. And that projectile motion is the same thing as the motion of the moon. That is an insight which changed the world. So there is always this joy of knowing for the first time what nobody knew, understanding something new, creating something new is a satisfaction that is unbeatable. But it is a difficult journey and you have to be prepared for it emotionally to be doing it. But I can assure you that if you take up that journey, there is no other pleasure in life that exceeds that journey. That is one of
Absolutely.
that by being a scientist is one of the most satisfying professions in the world. And which branch of science you want to take is up to you. And it should be left up to
Absolutely.
your emotions.
Absolutely.
What your parents should check is that are you willing to make the kind of emotional commitment you need to in order to achieve that. And as far as mathematics, there was a time when mathematics jobs were sparse. These days, it is very different. I know somebody who did PhD in mathematics and then walked into a bank and said, "Look, I have done PhD in mathematics. How difficult can your mathematics be?" And they promptly gave him a job in the bank, and he's doing now extremely well. And he's probably earning 10 times as much as he would have earned as a pure mathematician. But he doesn't get to do any R&D at the level at which a pure mathematician. So somewhere you have to choose in life.
Very valuable words. A quick note to all the viewers who are joining in late. We are in conversation with Professor Mayank Vahia. Emotional commitment, mental commitment, and the way you do, you can take up everything. Last question from Raghav sir. He is asking constantly that what is a steady state theory?
So the universe exists. We know the universe exists. We can see stars, we can see galaxy, etc. The question that was existing in early in the 20th century was whether everybody is stationary with respect to everybody else, or is the universe expanding, or is it falling back? Now, the problem is that gravity is an attractive force. It only attracts, unlike electromagnetic force, which is attraction and repulsion. So you can make a stable structure like a crystal. In gravity, you cannot make a crystal structure because everything is attracting everything else. So the universe has to be in constant motion in order that you don't collide. So, for example, if the Earth starts spinning around the sun, we would simply go and bang into the sun. Or if we move too fast, we would simply fly away from the sun. So the problem with gravity is it has to be continuously moving. And people said that if the universe is stationary, it means everybody is moving with respect to everybody else. But like the solar system, everything is stable. And that was called the steady state theory, that the universe is stable and steady. And even if motions are required to sort of make sure that you don't bang into each other, those were also stable and steady. And like solar system, which has been around for what 4,500 million years, the universe also has been around since infinity and will live to infinity, where everybody will move only enough to survive gravity. And that was called the steady state theory. Then came the famous observations of Hubble, which said that the universe is expanding and that it is expanding at a certain rate. And we know 13.7 billion years ago, everything was at the same place at the same time. So even though steady state seemed to be a better, more attractive theory, satisfying theory, it turns out that the Big Bang theory seems to be more accurate theory compared to steady state theory. There are people who are still wondering whether you can sort of have what is called quasi steady state theory, where even though material is running away from each other, new material gets created which replaces the old one, and the universe remains to be steady. But there is not too much evidence to support that idea. So currently, there was a time when steady state theory was thought to be better than Big Bang, but now we have overwhelming evidence about Big Bang. So we think the universe is not in a steady state, but in an expanding universe. Okay.
Right, sir. Thank you. Thank you very much. So, just to tell all the viewers that, okay, just one person is asking constantly, just a second, below the steady state theory. Okay, he's asking that my actual question is expanding Universe is like impurities moving with flowing water. Impurities
That's
is
what I said. The universe is
like,
not a flowing liquid. The universe is an expanding in all three dimensions, all four dimensions of time also, and
mhm.
creating its own space-time as it flows. So it is not impurities moving in a water. It is like a cake that is fluffing up in an oven. It is
Right, right,
creating its own space and time as it
right.
expands. It is not a
Absolutely.
fluid flowing.
Absolutely. So thank you very much for your time. I think that it has been one of the best podcasts with asking and answering all the questions. And I think, sir, if time permits, next month we have one mathematics and symmetry that is even interesting and a
Sure.
very on a philosophical ground. So just to tell you, the viewers, we are not letting Mayank sir go because we are now on the row of doing two more podcasts coming up in the next month. And the second podcast, I won't announce it right now. It is going to be very interesting. It's a very deep philosophical podcast. It would be on the certain properties of mathematics. And as you can see, this great person would be explaining very deep, intricate mathematical symmetries. And I think it is going to be an absolutely fabulous podcast. So just stay tuned for that. And with folded hands, thank you, Mayank sir, for your time. It has been amazing. And I think also you enjoyed the show, isn't it? Because there were a lot of
Yes,
good
I
questions.
enjoy talking. Yes,
Yeah.
yes.
So these are the
Okay,
compliments coming up. Thank you, Mayank sir.
my
And
pleasure.
yeah, NGR Neo is telling thank you for your time, sir. So, sir, thank you very much for your time. Okay, just one thing, sir, quickly. So, he's asking that, sir, is expanding thing always need to grow in all dimensions?
Well, time is always growing, and you can have a rod which is heated from one side, which will increase only in linear direction with time. So all dimensions, all expansions don't have to be four-dimensional. They can easily be two-dimensional, one of space and one of time. But time
Thank you.
is essentially intrinsic
Right.
to it.
And Mazin Lab is also saying, sir, thank you to you, sir, and you
Okay.
also. So, sir, I know you are tired. So, with all due respect to you, thank you very much. We will be,
Thank you.
waiting eagerly for your next lecture coming up next month. Rudrasi is also
Thank
telling, nice lecture, sir. Thank you very much.
you.
And stay tuned for the next lecture of Mayank sir coming up in the month of June. And in this month, on the 25th, we have another podcast coming up from a researcher, Dr. Part from Sao Paulo, Brazil, which will be on naked singularities and black hole. With that, I would like to give again a heartfelt thanks to Mayank sir. It has been more than 1 hour 40 minutes, and he has been terribly busy. Thank you, sir. Thank you very much. And
Thank
we
you.
are
Thank
indebted
you
to
very
you,
much.
whatever you have said. Thank
No,
you, sir.
it's my pleasure entirely. Thank you.
Thank you, sir. Sir, please don't disconnect.
Okay.